Hey there, in this video I want to talk about using an adaptive step size. So previously we've used step size h, and we would set it small enough to get the results we want. And what is not all that unusual is that your equation or system of equations just has some tiny region where you need a small h. And unfortunately, that means you have to use a small h everywhere if you're going to have that part of your solution be accurate. And that means you waste a lot of time. The alternative is you use a big step size everywhere, and then you just completely ruin that part of the solution. It's just junk. So what we're going to do here is talk about, well, how can we have our code calculate its own step size to reach some kind of target accuracy for us? And we're going to call that target accuracy lowercase delta. By definition, it's going to be an error divided by step size. And so to estimate our error, we're going to use an idea that we last saw when we talked about integrating and calculating the errors when you do a numerical integral. Your basic idea is compare taking two small steps to one larger step. So imagine we're using the Runge-Kutta method. So if we take two steps using the Runge-Kutta method, then what we could say is that x is equal to x taking two Runge-Kutta steps, and we're going to have, so x is the true value, and x, h plus h is our numerical value after taking two Runge-Kutta steps, and the difference between those is going to be 2 times the error, and it's a 2 here because there's 2 steps. And for a fourth order Runge-Kutta method, our error is fifth order. So it's going to scale like h to the 5th power, where c is some unknown constant. I mean, if we knew what c was, we'd know what our error was, and we would just add it on to our original, and we would have a perfect solution. But of course, that's impossible. But it scales as h to the 5th. So if we plug that in over here, we could say that the true value is equal to our estimated 2-step value plus 2 times ch to the 5th, where again, we don't know c. Now, if we compare that to doing one step of the same total size, so this would be a step of size 2h, then compared to the true value, we have our numerical value, and then it's going to have some error term that's going to scale like c times 2h to the 5th. And if we multiply that out, I mean, 2 to the 5th is 32. So that's going to scale like 32 times ch to the 5th. Okay, so now what we can do is we can say x equals x. And if we set those two equal to each other on the left-hand side, we have 2 small steps plus 2ch to the 5th has to be equal to 1 double step plus 32 ch to the 5th, which gives us then the double step, or the 2 steps minus the double step, is then equal to 32 minus 2 is 30 ch to the 5th, or we could write that as 30 times our error epsilon. In other words, let's come over here, our error would scale like 1/30th something we can measure. So we calculate these 2 different steps. We do 2 small steps versus 1 big step, subtract them, divide by 30, and that gives us an estimate for our error. Now keep in mind, this is an order of magnitude estimate. We can't say that this is exactly our error, because that's the whole idea, is you don't know what it is. A second thing here to watch out for is we are going to take the convention that our error is always a positive estimate. So we're going to make this an absolute value here to guarantee that we get a positive number. Okay, so we have this error estimate, and it's this term right here. Now, meanwhile, we are trying to have an adaptive step size to maintain an ideal error. So the ideal error, we'll give those ideals a prime, is going to be this epsilon prime, and that is, by definition, going to be our target accuracy times our ideal step size. And we could also write this as c times h prime to the 5th power, since the error scales like h to the 5th power. So let's go and divide both sides by the error that we just found. So and by both sides, I mean this stuff here. So I'm going to take delta h prime and divide by the epsilon. And on the right-hand side, I'm going to have c times h prime to the fifth divided by epsilon. And since epsilon itself scales like c times h to the fifth, that's going to be c to the h to the fifth over here. And then we can cancel out the c's, and we get h prime on h to the fifth. Okay, so delta h prime on epsilon scales like h prime on h to the fifth. And so if we rearrange this algebraically with the goal of solving for h prime, we're going to get that h prime to the fourth is equal to h to the fifth times delta on epsilon. Okay, and then to solve it, we need the quarter root of both sides. So on the left, we're just going to have h prime. On the right, we're going to have, we could write this as an h times h delta on epsilon, all those things to the 1/4 power. All right, so that is the ideal step size where we have a way to calculate epsilon. We choose delta as a target accuracy, and then h is the current step size. H prime then being the new better step size, whether it be larger or smaller. And whether it's larger or smaller then depends on this term in parentheses here. So putting this all together is going to give us a recipe we can follow to keep adjusting our step size. So step one is going to be, we're going to pick some h to start. So we're going to start with some really small value of h. And the reason I want a small value of h is I want to make sure that the very first step I take is itself very accurate. And then the idea being that this is smaller than you expect it to ever need to be. And then your method will then make the h grow to a comfortable size from there. So to start calculating what you're going to need, you're going to have to find some things. So you're going to use the Runge-Kutta method a few times, a total of 3 times, twice to find this 2 small step size x, and a third time to find the double step x. And then with that, you can calculate your error as 1 on 30 absolute value of the difference between those 2 estimates. And then with that, we can then calculate whether our h grows or shrinks. Now here we have to make some decisions. So if it turns out that h was smaller than it needed to be, this is okay. We can keep that result and keep going with the bigger h. However, if h was too big, we don't want to keep that result because we're already starting to be less accurate than we want. So we need to test here. To do this test, we're going to calculate the term in parentheses down here, because this is what determines whether our step size grows or shrinks. So let's call that rho, and that is equal to h delta on epsilon. And if rho is greater than or equal to 1, then we were good. Right, that means that our step size has to grow, so we can keep the existing step size. Yes, it was smaller than it needed to be, but we can still use it. We're just more accurate than we wanted. Nobody's going to complain about being more accurate. And so we can keep the step, and now we'll calculate a new h using the old one and then the rho to the 1/4. That's just the same thing as the boxed equation. Now there is one thing we have to be careful of here. It could have been, since we're working numerically, it just could be, if we're really unlucky, that these 2 x's were the same number, or extremely close to the same number, which gives us then an epsilon of effectively 0. When we calculate rho, we get infinity, and that means we have to grow our step infinitely, which is, that's a bad idea. It's a really bad idea. So what we're going to do is we're going to limit it to twice h. So we'll say we're going to limit to doubling. And that's, whether it be limited to doubling or tripling or times 10, that's kind of a matter of preference, but the most popular choice here is to go with doubling. And so because if you double, it doesn't take too many iterations to get very large, if that's what the function needs to do. So it doesn't really cost you very much, and it's not such a big change that it's likely to mess up your solution. Okay, so that's if rho is greater than 1. Otherwise, so meaning that rho is less than 1, then we have to reject the step. We don't keep that result. Instead, we just immediately calculate a new smaller value of h using the same equation. Since rho is less than 1, this will make h shrink for us. And then we repeat until we reach the end of our time range. At every step, we are setting x to a new value. And we have two choices. We can set it equal here to the double step, or the two steps, or the double-sized step. The better one is going to be the two little steps. This is always going to be a little bit more accurate because it's made out of smaller steps. And then for our time, we're going to do increments of 2 times h, because we're to be consistent here. So this is 2 little steps, so we have to make sure we're adding 2 of those time units onto our time. So one more thing to cover here is how do we change this method if we have simultaneous equations? In particular, what do we do with our errors here? So like if we just have an x, clearly this is the error in x. But what if we have x's and y's? What do we do? Well, there's 2 strategies that come up. Sometimes you only need your solution to be accurate for a particular variable. Maybe you only care about x's being accurate and the y's, they have to be consistent with the x's, but they don't have to be especially accurate themselves. In that case, you don't change anything in this method. You just use whichever variable is the important one. Like they'll usually be like the one you're plotting. But let's say that they're both important. In that case, what you do for your error estimate is you add the errors in quadrature. So let's say that you have an error estimate for x, which would take this kind of form here. You have an error estimate for y. Then your overall error would be those 2 added in quadrature. So that would be the x error squared plus the y error squared square rooted. That would be your total error, and that's what you would use here in place of just the single variable error. Okay, so now let's go over to the notebook and try things out. Okay, here we are back in the notebook. Let's try an example. We're going to do the pendulum again. So as a reminder, that was a second order equation. d2 theta dt squared equals negative sine theta. And in Python code, that looks like this. So we take R here as an array that contains both theta and the angular velocity omega. We unpack those, and then we have functions to return the right-hand side of 2 simultaneous first order equations where d theta dt equals omega and d omega dt is this right hand side from up here, negative sine theta. We put those together into an array to return them. Okay, so now the rest of our code here is going to make this use an adaptive step size. We need to define some parameters. The first one is going to be delta. That's our target accuracy. Let's say I want an accuracy of 1 part in 100,000. And so that means I have to be 1 part in 100,000 per step. That's radians per second is my accuracy units here. Now, before, when we did problems like this, we would create an array called t-values, and we would know exactly what time values we were going to use because we had a fixed step size. If we're going to have an adaptive step size, we don't know the time steps ahead of time. Instead, what we can say is what maximum time do we want? We start at some initial time, and in this case, we'll start at time 0, and we're going to end at some maximum time. Let's do 20 seconds. And so our code will take steps until it reaches 20 seconds or tries to pass 20 seconds, at which point it'll stop. We need some initial value for h, but h is going to change throughout this code. You want to start with something kind of small. If you take too big a step in the first place and you sort of step outside of where your function is going to be, you might be really accurate outside of that, but you will have effectively messed up your initial conditions. So always want to start with something that you're sure is plenty small. We were able to do this problem pretty convincingly with, I think it was 0.01, so we'll go even 10 times smaller than that. And then our method will just adjust h as it needs to. So what we're going to do now is we're going to make some empty lists. T-values is going to start out as an empty list because we don't know the time values yet. We're going to fill it in. We're going to have a list for our theta values, and we're going to have a list for our omega values. Although at the end of all of this, I'm only going to plot theta. I'm not going to plot omega. I mean, you're welcome to if you want to, but I'm not going to actually use it. I'll keep it in the code anyway, though. So now we are ready to create our loop. We start with some initial conditions. T equals 0, theta and omega equal, let's make theta 3.1, sort of like the most extreme thing we tried with a slider in an earlier video. We'll see if it looks the same. And we'll make the initial angular velocity 0, representing releasing the pendulum from rest. And now we're going to create a loop. Now before we used a for loop because we knew how many time steps we were going to take. Now I want to use a while loop because I don't know how many time steps I'm going to take. I'm just going to keep taking steps as long as the current value of time is less than its maximum value. Now inside this loop, the code is at least initially going to look very similar. We begin by appending old values. So we are going to append t into the t values, theta into the theta values, and so on. And now we have the recipe here for making stuff adaptive. We are going to calculate a parameter called rho. And we are checking here if rho is less than 1 or greater than 1. And so while rho is less than 1, this means that our step size is bigger than it needs to be. Or, wait, I got that backwards. If rho is greater than 1, then our step size was smaller than it needed to be, and that is fine. It's a little wasteful, but our results are good. We can keep going. If rho is less than 1, then that means our step size was too big. We have not hit our target accuracy. We have to reject that step and create new ones. So the reason I set rho equals 0 here is to guarantee that we will trigger this loop at least once, because we have to at least check once if our step was a good step. So inside this inner while loop, we need to do some things. One mistake that's really easy to make, one that I've personally made trying to write this example, is you want to make sure you stash your time steps. So every time we go through this loop, we have to make t values up here with the current time value. And so I need to know what the current h value was. And I want to do that first because I'm going to later on change h. And that's a, believe me, a painful bug to try to find. So first thing I'm going to do here is to stash my time values. Now, the way this method works is we need to take two tiny steps compared to one double step, and then we're going to use that to calculate an error estimate. So let's call the two small steps 1. So theta 1 and omega 1. So these are like steps of size 1. And they are the result of doing a Runge-Kutta step, giving that f, theta and omega, time and h, and then we take another one of those. So this will give us a total of 2 steps. The difference here is I want to make sure I'm using the intermediate theta and omega. I also have to be careful here to increase time by 1 amount of h. Okay, so after this step here, we've gone a total of 2h. So I'm going to add some comments here just to remind us of what these things are. So this is 2 small steps. And now we're going to compare that to 1 big step, 1 double step. So we'll call that theta 2 and omega 2. That's the result of taking a double step. So that'll be RK4. We want to give that f. We want to give it the original theta and omega. So we're like basically doing these at the same time. Compare them. T, and it's a double step, so this needs to be 2 times h. So this is 1 double-sized step. Now that we've done those, we can calculate the epsilon, our error estimate. We want an absolute value in here because we want positive errors. So theta 1 minus theta 2, and then we divide that by 30, like we just saw when we were writing it out by hand. We can calculate the parameter rho here as h times delta divided by epsilon, and this is what's going to get checked. Is this thing less than 1, in which case that was not a good step. Try again. Or is that greater than 1? It was a good step. Now, if we're going to try again, we need to check, or we need to create our new value of h. In fact, actually, no matter what, we want to calculate a new value of h so that either our steps are getting bigger if they were smaller than they had to be, or getting smaller if they weren't accurate enough. So the new h is equal to the old h times the parameter rho raised to the 1/4 power. Now, this line by itself actually is extremely dangerous because there is a non-zero chance that just, not really randomly, but as fate will have it, when you calculate theta 1 and theta 2, they are the same number. Even though there's some inaccuracy here, it could just coincidentally be that they both end up being the same number. That then tells you have an error of 0. That then tells you that your rho is infinite and your new step size should be infinitely larger than the old step size. And that's a disaster just waiting to happen. So what we want to do here is never ever get larger than some cutoff. And the typical cutoff here is twice h. And that way, if you need to make a bigger step, at most you'll double h. And if you keep doubling h a few times, that will happen plenty fast enough. This sort of saves you from things going crazy. Okay, and so that's what the min function is going to do here. If this ended up ever being bigger than 2h, you would instead choose 2h. Okay, and that will end the inner part, this inner while loop. So, this happens until rho is less than 1. We've got a good h picked. And then theta and omega are going to be equal to, we could, in principle, you could pick here theta 1s or theta 2s and omega's 2s. It's going to be more accurate to use the theta 1s because they are made out of 2 smaller steps, which in principle should always be more accurate than taking one big step. All right, so then finally, we want to take t and step forward by the amount dt that we've sort of stashed up here. Again, be careful about, you don't want to use this h because this is calculated after you've succeeded. So that would be, it's a small error, but it can start to add up. Okay, so that's the end of this top while loop, and we're ready to plot results and see what has happened. So we're going to plot our t values and our theta values. We're going to use dots for those. Let's see if this works. All right, so this is basically the same shape we had last time, right? So that's looking good, kind of smooth at the bottom. We did get this warning message. We'll come back to that in just a moment. But before then, let's look at how we've spaced out our steps. With the dots here, it's visually kind of hard to tell. So what can help us is if we plot some vertical lines at each point. And so there, Matplotlib has a command for that called vlines. The way vlines works is you give it an array of x values that you want to have a vertical line at, and you tell it what do you want the minimum and maximum y for each line to be. So in our case, I want to draw lines at all the t values. I want the lines to stretch all the way through my graph. So that would be from -pi to pi. Okay, and so with our lines drawn in there, we can see that where the pendulum is not moving very quickly, we don't need such tiny time steps because it's not doing very much. And when it's changing rapidly, that's where we need to spend our time steps. You also see right at the beginning here, we have a whole bunch of time steps. And that's not really set by the shape of the function. That is set by us starting with a very tiny time value and also limiting the fact that we can only double it at most. So it's going to take some amount of time steps to basically find what the ideal spacing is, and then it's going to go from there. Okay, so let's look at what happens now. I'll turn this part off, but let's look at what happens if I don't do this minimum stuff. So let me copy that line, and I'm just going to get rid of the min. Live dangerously, right? Let's see how it works. It is terrible. It's absolutely terrible. Why has that happened? Well, you notice that warning message that we got, not just this time, but last time, where it's like divide by 0. Like why are we dividing by 0? Where could we possibly be dividing by 0? Right here. What has happened is we've had one of those, miraculous events where theta 1 and theta 2 ended up being the same value. And it looks like it's right at the very beginning. It's like this very first time step where basically this is flat right here. And so taking a small step or a double step gives you the same value. And we end up then with epsilon being 0. We try to divide by that. It of course throws an error message. There's, I think, a step where we're close to this being 0, and we divide by that. It makes this huge number. We say, I want h to be, if not infinity, gigantic, and then everything's broken. It dies. So that's why it's really important to limit the growth of your steps. Otherwise, at some point, you just get unlucky, and you get this huge step and breaks everything.